Okay, so afternoon everybody. Welcome to the seminar this afternoon. I'm introducing Beniamino Iandolo, who's giving a presentation today. Ben is here with us as a practicum student for 6 months from Chalmers University, where he's doing his PhD in hematite materials for photoelectrochemical cells. And he's going to be talking about that in his presentation. I first met Ben at the conference in 2010?
Yes, in Obergurgl.
In Austria. In a very nice location in Austria, in the UNSW Valley, where the Iceman was found, actually. But and it's a very interesting conference, and Ben was talking about related work then, and looking forward to hearing more about that now. And I also met him at, in Lord Howe Island, when we had another conference on looking at photoelectrochemical cells as well, which was a very nice place to go to. But Ben did his first degree at Politecnica di Milano, finishing in 2007. Where he was studying engineering physics, and then went on to do a master's also at Milano in the same subject, before moving to Chalmers University, where he did a second master's degree on this subject, I think, wasn't it?
I was here as an exchange student, yes.
I was an exchange student,
yes.
Sorry. Before starting his PhD, also at Chalmers, in 2010. And then he's been working on hematite materials ever since then, and he's going to be telling us about those materials and about plasmonics associated with hematite. So thank you very much, Ben.
Right. Thank you, Gavin, for a very nice introduction. Good afternoon, everyone. And the title of my talk, as you can see from here, is sunlight-driven water splitting in hematite-based photoelectrochemical cells. Most of the work I will talk about here has been done in Sweden at the Chalmers University of Technology in Gothenburg, within the division for chemical physics at the applied physics department. So we can see from this picture the idea of what we have of a Swedish nice summer day. Anyway, here comes the outline of my talk, and I will be spending most of my time today talking about this. About this first part here. So Plasmon-enhanced water splitting of hematite-based model photoanodes. So a few words to introduce the field of Plasmon-enhanced water splitting. I'd like to start saying that when we're looking for some replacement for fossil fuels as an energy carrier, if you're looking for something that's also environmentally friendly, hydrogen is particularly attractive for a few reasons, but in particular for one, because it can be produced or mass-produced from water in a process called water splitting. And if the energy that is needed to take this process, to perform this process, is taken from a light source, for instance sunlight, we're talking about light-driven or solar water splitting. There are basically 3 kinds of devices which can help you perform in this task. We have the solar cells in series with electrolyzers, photocatalytic cells, and photoelectrochemical cells. And I've been working on the latter, which can be described in a few words as a monolithic device in which the oxygen and hydrogen are evolved from water at locations which are macroscopically different in the cell. So at this stage, I'm not quite sure how many of you are familiar with the working principle of photoelectrochemical cells, probably a few. Yet I would like to spend a few words to describe the working principle. So in most photoelectrochemical or PEC cell, you will find 2 electrodes, which are immersed into an electrolyte. At least one of these electrode is made of a material which is able of absorbing light, typically a semiconductor. And this is why it's called a photoelectrode or working electrode. If the photoelectrode is made of an N-type semiconductor, we call it photoanode. And it turns out it's usually composed of a light-absorbing material and a charge conduction layer. On the other hand, we have the cathode or the counter-electrode. Typically is composed of graphite or platinum. And also in most research used PEC cell, we also have something called a reference electrode, which helps us having an accurate value of the electrochemical potential at the surface of the working electrode. So these are the reactions that take place at the surface of the anode and the cathode, where oxygen and hydrogen are evolved respectively. And let's see now what happens if a photon of appropriate energy, that is equal to or higher than the band gap, enters the cell and it's absorbed in the light absorber. What happens then is that an electron-hole pair is generated, and these charges can be separated by the built-in field that is present at the interface between the working electrode and the electrolyte. The charges are separated, they take different ways. The hole will travel towards the surface of the photoanode, whereas the electrode will travel towards the surface of the cathode via an external circuit. When we have 4 of these events, and all 4 holes have reached the surface, they can take part in the oxidation of 2 molecules of water, thus producing 1 molecule of oxygen. Meanwhile, the protons travel via diffusion through the electrolyte, they reach the cathode, and a hydrogen evolution can then take place over there. When it comes to determining the total energy conversion efficiency of such a device, it is important to realize that such efficiency is given by the product of efficiencies of the single steps that I just described. So light collection, charge separation, charge transport within the light absorber, charge transfer between the absorber and the electrolyte, and reaction selectivity, in this case for oxygen and hydrogen evolution. And these requirements are typically impose limitation on, or requirements on the light absorber, and without going too much into detail, there are actually more of them regarding not only efficiency, but also durability and fabrication costs. So the research I will tell you about today is about a particular kind of light absorber for this type of cells. And material we've chosen is iron oxide, or a particular form of iron oxide known as hematite. Please. Hematite is considered very attractive for water splitting purposes because, for instance, it can absorb visible light thanks to its band gap of around 2 electron volts. It's very inexpensive, and it's stable in aqueous environment for pH larger than 3. On the other hand, we can see, for instance, that the band alignment between the conduction band of hematite and the proton reduction potential is not optimal, which means that in order to achieve complete water splitting, we need to apply a certain electrochemical bias, typically in form of an applied voltage, and this reducing our efficiency values. Furthermore, hematite has an indirect band gap, which means that the efficiency for light absorption is small, especially close to the band gap. And perhaps most importantly, hematite is known for being a poor semiconductor, so low electron conductivity, and perhaps even more importantly, very short hole diffusion length of about 4 or 5 nanometers, which means that if the holes are not generated and then right away driven towards the surface, they will not be able to take part into the water splitting reaction because they will undergo recombination. So there is a whole lot of research in trying to alleviate this mismatch between hole diffusion length and photon absorption length. And the main goal here is towards achieving a photoanode which is physically thin, so charge transport are not the main limitation, but optically thick, so we can absorb as much light as possible. And there are 2 main strategies to achieve this goal, in fact. The first one is to nanostructure the absorber, and there is a whole lot of literature around it where people try to fabricate different geometries and shapes and all sorts of things like that. I'm not going to focus on this, though. What I will talk about is what we have been working on, which is enhanced light absorption in very thin films of hematite, typically 20 to 50 nanometers, by functionalizing them with metallic nanoparticles. And we know that metallic nanoparticles can help us in our case because they can be very efficient at scattering or absorption light, or absorb light, when a particular phenomenon called localized surface plasmon resonance takes place. And in a few words, this is more or less a collective oscillation of the electron in the conduction band of the metal nanoparticles under the influence of an applied electric field. And the electric field can be, for instance, the one carried by photons. So this in a few words. Someone has any idea when the first example of applied plasmonics was ever made? No idea? 50 years ago? 100 years ago? It was around 300 years after Christ. And it is known, you can actually go there, have a look in the British Museum in London, and it's what we call Lycurgus cap. This cap is particularly interesting because it basically changes color depending on whether it's illuminated from the outside or from the inside. So on the left picture you see a cap illuminated from the outside, on the right side the cap illuminated from the inside. And what happens here is the following. The glass which composes part of this cap contains a lot of silver and gold nanoparticles. And these metallic nanoparticles are very efficient, once again, in scattering light. They're particularly able, in this case, to scatter blue light. So that the end result is we see the cap as red. As now known in the literature, the wavelength or energy or these excitations or these localized plasmons do not only depend on the metal, but also on the shape. If we have two nanoparticles with the same amount of material, different shapes will lead to different position of this plasmonic peak. Size, typically redshift for increasing size. And also refractive index of the nanoenvironment. Typically, once again, the higher the refractive index, the more the main peak will be redshifted. The other main characteristic of such resonance is that when it takes place, the electric field around the nanoparticle is highly, or the configuration of the electric field around the nanoparticle is highly changed as compared to the incident field. And we'll see how important this is in a few minutes, actually, in our case. So something about the plasmons here, but how can these resonances help us in our case? So how can they help improving the photoelectrochemical properties of hematite? We have four main mechanisms that can actually take place. The first one is a so-called far field effect. And if we assume, as I will do in the remainder of the talk, a configuration where the metallic nanoparticles are placed at the interface between the hematite and the water. So these nanoparticles can scatter light into the hematite, thus prolonging the optical pathway and thus enhancing the probability for light absorption. The second mechanism is a near field driven enhancement. And it has to do with the fact that if the field enhancement that I mentioned before extends from the nanoparticle into the hematite, this can lead to enhanced carrier generation within the semiconductor. The third mechanism is so-called the hot electron injection. What I mean here is the following. These collective oscillations have a certain lifetime. And when they decay, they can do it generating a single electron-hole pair oscillation. And if the band alignment between the metal and the semiconductor is proper, the electron can actually be injected into the conduction band of the hematite. If this doesn't happen, most probably the electron-hole pair will thermalize and generate heat within the nanoparticle. But if the situation is proper, it could also happen that heat can be transferred from the nanoparticle into the semiconductor, thus again enhancing in principle the conductivity. The configuration I mentioned before is the same we've been using for all our photoanodes that I will show the results of now. And I would like to point out at this stage that what we've been working with is something which we call photoanodes. We are mostly interested in studying a little more systematically what is found in literature, the influence of these metallic nanoparticles. And on the other hand, we're not really much after the highest efficiency from these photoanodes themselves. So the fabrication procedure is rather simple and is divided in three main steps. What I would like to spend a few words on now is this last step, how we functionalize the iron oxide, the hematite. We do this by putting on top of the hematite gold nanodisks. And we chose gold mainly because gold is known to be able to support plasmonic resonances in the visible, even when surrounded by dielectrics and water, which would redshift this spectrum. And this is particularly interesting because we can then overlap the absorption spectrum in the nanoparticles and the absorption spectrum in the hematite. And why do we choose nanodisks? Well, it's actually a result of the fabrication process we use, which is called whole mass colloidal lithography. Some of you might actually be familiar to a similar process called colloidal lithography. And this is nothing but an extension of the original method, developed at Chalmers, actually. So I will navigate you through the steps which lead to the fabrication of one such functionalized sample. First, we start by spinning a layer of sacrificial resist. Any photoresist would normally work. We typically use PMMA. And then we adsorb on the surface a monolayer of aluminum chlorohydrate, which is electrically charged. And then we pipette and then blow dry a solution of polystyrene nanospheres, which are electrically charged as well, just with opposite sign compared to the ACH. So they will like to absorb on the surface, and on the other hand, they won't like to be too close to each other due to electrostatic repulsion. So what happens is, at the end, we have a distribution of nanospheres that are somehow short-ordered on the whole surface. Then we use physical vapor deposition to evaporate a thin mask layer, typically chromium, but anything that can survive oxygen plasma can work. And then we use normal tape, actually, to strip away the nanospheres, leaving a film of chromium with holes where the nanospheres were previously. Then we use plasma etch to drill basically holes down the PMMA, all the way down to the hematite. And at this stage, the sample is ready for depositing the material we would like to deposit, in our case, gold. Also, we have here around 5 nanometers titanium layer, which serves as an adhesion layer. And it basically prevents our gold nanodisk to peel off from the surface while characterization. So with this technique, you end up having a short order arrays of nanostructures, and it turns out you can control with a higher degree important properties like shape of your nanoparticles. You can, shapes like cones, rings and stuff have been demonstrated already. You have good control on size, surface coverage, and chemistry. So back to our hematite films. Our XRD analysis show that with the fabrication process we obtain polycrystalline films, and the only observable phase is hematite. And at this stage, it might be interesting to know the bandgap, actually, because I haven't told you so far, but the bandgap value for hematite ranges from actually around 1.8 to 2.2 electron volt. So it's definitely interesting to know where we end up in our case. So what we use is to measure the absorption coefficient for films of different thickness, and then we use standard tau analysis to determine the value of our bandgap, which is indirect and is actually a little bit depending, or slightly depending on the thickness of the film. We can see here that the thinnest film turns out to have a slightly larger bandgap. We haven't investigated this in detail, but we think it might be related to different levels of stress release between the ITO and the hematite film on top. As you can see from these extinction plots, by putting down the gold nanodisk, we do have a difference in optical extinction, which is nothing but the sum of absorption and scattering. And if you plot the difference, it becomes clear that in each of these samples, the plasmons are indeed excited in the gold nanodisks. And we can see that the main plasmonic peak is shifted towards the red for increasing hematite thickness. And this is an expected phenomenon, and this is due to the fact that the more hematite we have underneath the gold nanodisks, the higher the average refractive index around the nanoparticle will be. And that's because hematite is known to have a higher refractive index than ITO. On the other hand, we also see a shoulder, at least for the 25 and 55 nanometer thick hematite films, and I will come to the origin of this in a little while. The first test in order to check for the photoactivity of these films is to do photocurrent versus potential characteristics, and we've done this in a standard 3-electrode configuration under solar simulated illumination. What you see here, activity is practically negligible for both reference and functionalized films under dark. These are photocurrent curves for the reference samples with illumination. And you can see it by putting on the gold nanoparticles, we have a dramatic increase in photocurrent. From this measurement only, however, we have no clue on where spectrally the improvement that we observe is actually localized. In order to gain more information on this point, we performed wavelength resolved photocurrent measurements, from which we can calculate the IPCE, or external quantum efficiency. And what you see here is a plot of efficiency difference between, once again, the same functionalized and the same reference samples. And the plot here, by comparison, the measured extinction difference in the same spectral window. So if you go here from longer to shorter wavelength, we see at first, right after the band gap, the photocurrent starts to increase, thus the efficiency starts to increase, and we can see there is a relative maximum in the IPCE difference. And this is highest for the thinnest film, which also showed the highest photocurrent as a function of potential before. And also the spectral position of this peak is red shifting as a function of hematite thickness, just as for the optical extinction. On the other hand, if we go yet to shorter wavelengths, we indeed see yet a higher increase. This is actually the highest effect. And I will come back to that later, because this is what we don't have a clear understanding of yet. What we think we have a clear understanding of is this Plasmon-rated improvement, and this is why I'm going to spend a few words now. So which ones of these mechanisms are actually responsible for the improvement we see? What we've done at this stage was to combine experimental effort with calculations. These calculations were done at, again, at Chalmers by my colleague Tomasz. And he uses FDDT calculations, taking into account all the layers that are found in the real sample as well, from the water electrolyte down to the bore float glass substrate. And what we can calculate, for instance, is the same optical extinction spectra as we measure. And by comparing the two, we see that the main trends I was mentioning before are actually saved, both in terms of redshift on main peak as a function of hematite thickness, but also as presence of the shoulder, which is somehow less pronounced for the 40 nanometer thick film. On the other hand, we do see differences. The position of the peak is not, of the main peak is not really the same, and the experimental peak are actually narrower, whereas usually is found the other way around. Calculated peaks tend to be narrower than experimental ones. And we do not have yet a full understanding of this, but we think that this is at least partly related to the fact that at the interface, the interfaces in the real samples are not as ideal as one is in the calculations. For instance, we know that at least part of this titanium layer gets oxidized during fabrication, also during characterization, even though the crystallinity or even the stoichiometry of this oxide is unknown, and it's therefore hard to model. And this is why Tomasz kept on using titanium layers for his calculations. What he can do as well is to map the electric field enhancement around the nanoparticles and the hematite. So what you see is just plots of electric field enhancement as a function of wavelength for a 25 nanometer thick hematite with the gold nanodisk on top. And we see that the plasmon actually starts to be excited already at 550 nanometers, right where this shoulder starts to appear. But in this case, the field enhancement is concentrated around gold nanodisks, which basically means it cannot help in any way in, or it cannot help in any way improving the performance of our hematite. But on the other hand, when increasing the wavelength, the electric field enhancement is drawn more and more into the hematite. And this is actually the same case for both 40 and 55 nanometer thick sample. If you actually focus for a little on this first row, we see that the enhancement around the top of these disks for the 40 nanometer film is slightly lower than in the other two cases, and this correlates well with the fact that we don't see such a pronounced shoulder in this sample. So what happens now if we take the value of the field enhancement in this region here, in the hematite, close to both the electrolyte and the nanodisk, and we plot them as a function of both wavelengths and iron oxide thickness. So what happens is the following. First, we see that for increasing iron oxide thickness, the position at which the maximum enhancement in the electric field is redshifted, and also the value, the maximum value of such enhancement decreases, just in good qualitative agreement with what we observe in the experiments where we determine the IPCE differences. And this points at a possibility to assign the increase due to plasmons to an enhanced charge generation in the hematite upon excitation of the plasmons in the gold. How do we rule more accurately, though, the other possible mechanisms? In order to rule out light scattering, Thomas has done additional calculations where he basically simulates the configuration of the scattered field outside this geometry. And it turns out this field is at least one order of magnitude lower than the near field around the nanoparticles, which leads us to be able to exclude light scattering. For what concerns auto-electron injection, we have done a test where we just replace the titanium oxide layer with fully oxidized silicon oxide, and we see that the IPCE different curves basically doesn't change. So this makes us think that in our case, electrons do not have the possibility to be injected from the gold into the hematite, thus ruling out these mechanisms. And finally, for what concerns heat, additional calculations were done by Professor Zdanov, also at Chalmers, where he basically simulates the or models the transfer of heat between the gold nanoparticles and the hematite. And his conclusions are that under solar simulated illumination, the increase in temperature is practically negligible. We're talking about 10 to the minus 3, 10 to the minus 4 Kelvin, actually. So we can rule out this mechanism as well. And we are left with the mechanism I mentioned before, so near field enhancement in the nanoparticle leading to enhanced charge generation within the hematite. So this concludes the first part of my talk. The other two will be shorter, and I will start with a few words on our determination of the Faradaic efficiency for oxygen evolution on hematite. These experiments were done in collaboration with our colleagues at DTU in Denmark, using a fairly similar setup to the one we usually use at Chalmers. And the main question we wanted to answer here is how much of the charge that we measure in a normal photocurrent experiment actually goes into oxygen evolution. In order to do this, or in order to determine the Faradaic efficiency, as it's normally called, what we've done was the following. First, we have measured the photocurrent as a function of time for different reaction times. And upon integration, we have obtained the total charge. Then we've used gas chromatography to analyze the reaction products and extract the amount of oxygen which was due to the water splitting reaction. And the corresponding charge was compared to the total charge. And you can see here the results. Basically, for both reference and functionalized sample, in this case, both are of the thinnest thickness we have, they both show, within experimental errors, a Faradaic efficiency of around 1. And if this is true for solar simulated illumination, it must be true also at each single wavelength, also, for instance, at which the plasmons are excited within the nanoparticles. So for this experiment, we can conclude that all the charge that we can detect is actually going into oxygen evolution and water splitting. Also, since the stability of these plasmon-enhanced photoanodes has not been investigated in detail in literature, we also thought of doing a stability test, not so long, but still around 16 hours reaction time of one of our functionalized photoanodes. And we can see here that after a certain transient, the current is stabilizing and does not drop over the whole remaining of the experiment. And still after 16 hours of reaction time, the Faradaic efficiency is basically 1, again, within experimental errors. Finally, a few words now on beyond plasma-enhanced water splitting. And this brings me back to the question I left aside before. So when we consider this highest enhancement of efficiency at short wavelength, what is or what are the mechanisms behind? And by just making a very crude experiment where we just have a sample where we compare the activity of samples with titanium and gold with a sample with just titanium, we see that the adhesion layer is likely to play at least a role. And that's because we can see that while on one hand the sample with only titanium doesn't show any plasmonic signature, we do see that it behaves practically the same as the sample with gold, at least up to 480 nanometers in wavelength. And so we think that the properties of the interface between the semiconductor and the electrolyte, and therefore the addition of anything to this interface, being a metal, being another dielectric, triple junctions, anything can actually impact considerably these systems. And when it comes to try to find a technique that allows us to study these properties, electrochemical impedance spectroscopy turns out to be quite useful. So without going into detail again into describing the technique, it's not much different from measuring a normal photocurrent versus potential scan. The main difference is we apply also an AC voltage bias, which allows us to record the total complex impedance of the system as a function of continuous bias and also frequency. And for each of these potential, you can actually build an Nyquist plot by plotting the real and imaginary part of the total impedance. And from these plots here, you can extract very useful information about the surface properties of the system, provided that you are able to come up with a good equivalent circuit models for the system you're studying. And this has been recently done in a few publications, actually. So the knowledge of this technique applied to hematite has been increasing over the past few years. For instance, it has been used to study the influence of surface states on the water oxidation properties, and also studying of the reason behind the improvement of efficiency upon covering hematite with this cobalt oxide or cobalt phosphite layers. What we think is lacking currently in literature is more investigation studies, though, on how these surface treatments are placing different metals or different dielectrics on top of the hematite can affect its photoelectrochemical properties. And this is our plan for our measurements here at SPREE, University of New South Wales. And we think that our fabrication process gives us an edge in terms of controlling surface properties of our sample in terms of chemistry, surface coverage, thickness of what we put on the hematite. So finally, we come to the conclusions. In this talk, I described how we fabricate our model systems consisting of ultra-thin films of hematite. I hope I convinced you that upon functionalization with gold nanoparticles, the properties are greatly enhanced, the efficiency is improved. And for what concerns the plasmonic increase, I hope I convinced you we can assign this improvement to the near field enhancement around the gold nanoparticles. We've seen that the Faradaic efficiency for oxygen evolution on this system is basically 1. And I've shown you some plans for future experiments to be conducted here at SPREE. Finally, I would like to acknowledge some people who, to various extent, have contributed to this work. First, my former supervisor, Michael, my current supervisor, Anders, my current co-supervisor, Igor, Matthias, who helped me setting up the photoelectrochemistry experiments at first, Björn, who helped me doing the same both at Chalmers and at ETU, and Brian and Ib for giving me the opportunity to perform my experiments over there. Thank you for your attention.
Thank you very much, Ben, for that very interesting presentation. We have time for questions.
Yes, so I applaud your use of electrochemical impedance. I think that would be very valuable. Are you just going to look at the hematite system alone with that, or are you going to look also with the gold nanodisks on too?
Well, I think our main focus now would be on trying to study a little bit in more detail the interface between hematite and typically other oxides, because we think we have a rather good understanding of what happens for the plasmonic part, and then at least when we have gold nanodisks. But it would be definitely interesting to try both.
So with these systems, what quantum efficiency do you assume for the hydrogen evolution at the cathode?
Well, we haven't really measured the total efficiency in a 2-electrode setup, which would give you more reliable results. For what concerns state-of-the-art efficiency, I think we are around 1.52%. And the target is, I think, around 10. But for this system, once again, we haven't really tried to measure the efficiency in a 2-electrode setup because we know that it will be low. These films are undoped, which means electron conductivity is poor. They are flat. So it was more of a platform for us to study how the metallic nanoparticles work in combination with the hematite.
The other question I was going to ask, this band lineup, I mean, you alluded to it, but the solution is always a problem in these electrochemical, photoelectrochemical systems. And so you're applying a external bias to make it go. Is your external bias that you're applying consistent with the band offsets that you showed in that one slide? Remember you have that slide that shows the reduction, I forget, and has all offsets. So TiO2 works, but you can't absorb any light, but hematite doesn't work, and so you have to apply this external.
No, yeah, but we just apply the bias that needs to lift out the conduction band so we can achieve overall.
So is that consistent? Is that consistent? With the
I would say so.
You didn't actually show the pH in that particular slide, because you can shift the alignments with the pH. Was that pH 7?
No, it was for the first. It's. I've been working with either 1 or 0.1 molar potassium hydroxide. So it will be either.
Basic,
yeah. So it will be either.
pH.
Yeah.
Okay.
It will be either 12.9 or 13.5.
But it actually shifts the wrong way then if you move towards
neutral.
pH
Yes.
7,
Yes.
Yeah. May I just add something on that, actually? One of the reasons that Ben's here is he's working with Haijang on a combined device for looking at Haijang's working on photocathodes. And the possibility there is to combine the two and get a boost in the voltage from the two if they line up appropriately, potentially to overcome the redox potential of water. So that's one approach that might work to do that. I had a question actually. On with the titanium interlayer, the adhesion layer that you put in, you mentioned that it can oxidize in some cases.
Yes.
But the modelling is just looking at just pure titanium. Could you, or could Thomas, look at the possibility of using titanium oxide as the interface in the modelling? And also, could you actually deliberately use titanium oxide experimentally as well? The reason being that the high dielectric constant is known to give a good coupling for plasmonics to silicon, certainly, and I think that would be true for hematite.
Well, it did do some calculations where it tries to model this adhesion layer with a combination of, say, half perhaps titanium oxide or half titanium, and also change the relative amount of titanium and titanium oxide. And the reason why we prefer titanium is that it gives us a better correlation with experiments, because when we have pure titanium oxide, the main plasmonic peak does not shift as a function of hematite thickness.
Okay.
So we think that this layer, at least when it is based on titanium, is not completely oxidized. I haven't shown here, but if we use silicon oxide instead, which is more fully oxidized, we do not see the same shift experimentally in the optical extinction.
Okay. Yes, I'm not quite sure what that means.
But it's something we could also try experimentally, actually, at least in principle.
Any further questions? Well, in that case, I think we'll thank Ben again for a very interesting presentation, and possibly there might be a chance to do some more presentation later on when you get some more results on some of this work. So that would be interesting to see how this goes. So thanks very much again. So thank you.